Hello students, I welcome you all. So how are you all? I hope you all are doing good. So there is a next session or this is the next lecture of your chapter, magnetic effect of current. So we have already started the chapter. In the previous class or in the previous lecture, what we have learned that whenever a current flows through a wire or any conductor, then it produces a magnetic field around it. Then we saw what was the direction of that magnetic field. Yeah, or what are the properties of magnetic field lines that we have seen in the last lecture, and we have also seen that what is actually the direction or the composition of magnetic field around a closed coil or around a solenoid. So that things we have already covered in the last lecture. So in today's lecture, what we are going to learn, let's see. Yes, these are the topics we are going to learn in today's lecture. So see, these are the topics. We are basically going to see three things. First is a force acting on a current carrying conductor. Then we will see magnetic force on a moving charge. Along with conductor, we will discuss also magnetic force on a moving charge, and we'll see a rule which is known as Fleming's left-hand rules. So these three things we are going to observe or we are going to study in today's lecture. Okay, clear? Now see, suppose in the previous class what we were studying the current flowing through a conductor produces a magnetic field around it. So what was observed that that field which was produced around the conductor, if we place a magnetic material in that field, then that magnetic material was experiencing a force due to that field. That magnetic material was experiencing a force due to that magnetic field. So there is a scientist, which is known as Mary. Yeah, the name goes as Mary. He gave the conclusion that if the magnetic field produced around a current carrying conductor is giving a force on the magnetic material, then the magnetic material should also apply an equal and opposite force on that conductor. That was the logic given by the Andre Maria, that if the magnetic field produced around a current carrying conductor is applying some force on the magnetic material, then in reverse, that magnetic material should also apply equal and opposite force on the conductor as well. So that was the force observed, that there whenever current flows to a current carrying conductor, it applies a force on it. It applies a force on it which is known as magnetic force. To understand that magnetic force, experiment or activity was done. What was done in that activity was like that. This was taken, a stand was taken like this. This was a stand taken. Okay. And there was a small aluminum rod also taken. There was a small aluminum rod which was hanging horizontally. Like this by the two connecting wires, and these wires were connected to the circuit. These wires were connected to an external circuit having battery and a key and a rheostat as well, or you can say variable resistance. This was the complete circuit. So this was the aluminum rod kept hanging with the help of connecting wires. This is aluminum rod, and a horseshoe magnet was taken. A horseshoe magnet was taken like this, such that the direction of magnetic field was upwards. The direction of magnetic field was upwards. So what can I say? If the field or the direction of field is to be in upward direction, can I say this will be North Pole and this will be South Pole? So just above the rod, South Pole was placed, and below the rod, North Pole was placed, so that the direction of magnetic field is from North to South Pole. That is in the upward direction. So what we observe that when we switch on the circuit in the activity, as soon as we switch on the circuit, what will happen? Current will flow. Current will try to flow in the direction. Suppose current is flowing in this direction. So this is the direction current is flowing actually. Okay. So what was observed that in that type of motion, there was a force exerting on the rod. There was a force exerted on the rod. Yes, there was a force exerted on the rod, which was given by the left side, or I can say the deflection of the rod was towards the left. Now what we did, we just reversed the polarity. We now just reverse the polarity of the battery, then don't see what is actually happening here after changing the polarity. Now this is negative, this is positive. This is the circuit again. Yeah. So this was the polarity reverse. So when the polarity was reversed, it was observed that now the deflection on the rod was towards the right. Deflection on the rod was towards the right. Okay. So this was the first observation. Then what the experimental did, he just reversed the polarity of magnetic field also. He just reversed the polarity of magnetic field also. Initially, the magnetic field was in the upward direction. Initially, the magnetic field was in the upward direction. Now he reversed the direction of magnetic field to downward direction. So it was north pole, it was south pole now. So that the direction of magnetic field is downward. Direction of magnetic field is downward. So this is north, this is south. So that the direction of magnetic field is in the downward direction. So the whatever observations were observed in the case of starting, that whenever the field was upward, the observation which were coming in the case of downward field was just reversed. So there was a conclusion made that the magnetic force or the force acting on a current carrying conductor depends upon two things. It depends upon the direction of current. It depends upon the direction of current flowing through the conductor, and what else? It also depends upon the direction of magnetic field. It also depends upon the direction of magnetic field. Okay, so these were the two things which were observed in the experiment, that the magnetic force acting on any current carrying conductor is depending upon two things. One is the direction of current flowing through the conductor, and second one is the direction of magnetic field in which the conductor is kept. These were the things. Yeah. So this is something known as force on a current carrying conductor. That is the force acting on a current carrying conductor. That whenever any conductor or a part of a conductor is placed in a magnetic field, then a force is acting on it. Now you can see whenever a conductor carrying current is placed in a magnetic field, conductor experiences a magnetic field. So that we have already learned, that whenever a conductor which is carrying a current is placed in a magnetic field, then the conductor would experience a magnetic force. Okay. And what is written, that the direction of this force is always right angles to the plane containing both the conductor and magnetic field. So what was observed during the experiment, that there was something force acting in a current carrying conductor, and it was observed that the magnitude of that force, was maximum. Magnitude of that force was maximum when the current flowing in the conductor and magnetic field were perpendicular to each other. Current flowing in the conductor and magnetic field were perpendicular to each other. So that was the case when maximum amount of magnetic force was observed. And from there comes a rule which is known as Fleming's left-hand rule. Which will give us the direction of magnetic force. Acting on a current carrying conductor. Clear? This is something about force on current carrying conductor. The formula for force on current carrying conductor is given by this. If I talk about the magnitude of force acting on a current carrying conductor, it will be given by ILB sin theta, if you can see in this diagram also. This is the direction of force upward. This blue is showing the direction of magnetic field. This I is red color arrow is showing the direction of current. Okay. And theta is the angle between current and magnetic field, if you can see in this diagram. This is theta. Angle between current and magnetic field. So in F equals to ILB sin theta, what is I? Current flowing in conductor. What is L? L is the length of conductor. Okay. What is B? B is the magnetic field. In which conductor is kept. And what is the final term theta? Now theta is the angle between L and B, or you can say current and magnetic field. Okay, because the direction of L is along the direction of current only. So it is the angle between L and B, or you can say I and B, current and magnetic field, whichever you are comfortable with. Because the direction of length is same as the direction of current. Okay, we take the direction of length same as the direction of flowing of current through the conductor. So now it is clear that whenever a conductor is placed in a magnetic field, a magnetic force will act on it. A magnetic force will act on it, and the direction of that force will be maximum when magnetic field and current are perpendicular to each other. And also one thing, that the direction of that force, that magnetic force which we are talking about, is always perpendicular to the plane. Containing both current and magnetic field. Yes or no? Both current and magnetic field, or you can say both conductor and magnetic field. So in whatever plane the conductor and magnetic field are present, the direction of the magnetic force will be perpendicular to that plane only. That is the case. So this is given by Fleming's left-hand rule, that the direction of the magnetic force will be given by Fleming's left-hand rule. Now see, we are observing magnetic force on a moving charge as well. We have studied that whatever the magnetic force acting on a current carrying conductor, that will be ILB sin theta. Yeah, this is for a conductor carrying current I having length L and placed in a magnetic field B, such that angle between magnetic field and current, or you can say angle between magnetic field and length vector, is theta. So that is ILB sin theta. Okay. So if you can see, this force will be maximum when theta is equals to 90 degrees. As you know, sin theta is, or I can say sin 90 degrees 1. And maximum value of sin function is 1. So that's why I was saying this force will be maximum when the angle is 90 degrees. When the angle is 90 degrees. Magnetic force on a moving charge. So basically, whenever a particle having charge Q moves in a magnetic field with a speed v or velocity v and magnetic field b vector, so the force acting on it will be given by a formula which is a QV cross B. This is a cross product, or you can say vector product, which is given as QVB sin theta. So this is the force, magnetic force, or this is the formula for magnetic force acting on a charge Q moving with velocity v in a magnetic field B. Moving with a velocity v in a magnetic field B, in the angle between velocity and magnetic field vector. Angle between velocity and magnetic field vector is theta. So the force will be QVB sin theta. The force will be QVB sin theta. Done? Clear? This is the formula for magnetic force on a charge Q. And if the charge is negative, suppose I am talking about positive charge, and if the charge is negative, then the direction of force will be reversed. Whatever direction you are finding with QVB sin theta, the direction will be reversed. So actually, whatever you are seeing in this formula is the combination of two forces. Okay, this is the combination of two forces. One is the force acting on a charged particle present in electric field, that is given by QE, where Q is the magnitude of charge and E is the electric field. Okay, this QV cross V is something which are concerned with us, yeah, which we are concerned with, that what is the magnetic force acting on a moving charge, that will be QV cross V, or the formula will be QV sin theta. Yeah, so it is written here that the force exerted on a charged particle Q moving with velocity v through an electric field E and magnetic field B. So this combined force is something known as Lorentz force. So Lorentz force is the combination of electric force and magnetic force on a charged particle Q moving with velocity v. So this you can see, this is the motion of a charged particle. This is the motion of a charged particle. The velocity is along the curved path. This cross is showing that the magnetic field is into the paper. This cross shine is showing that the magnetic field or the direction of magnetic field is into the paper. So whenever any charged particle minus Q is moving with a velocity v in a magnetic field going into the paper, then the direction of magnetic force will be towards the center. Then the direction of magnetic force on that charged particle will be towards the center, and that center force will give him a centripetal force so that it will be able to do a circular motion. It will be able to do a circular motion. So whenever any charged particle enters in a magnetic field perpendicularly, whenever any charged particles enters in a magnetic field in a perpendicular direction, then that will do a circular motion. That will do a circular motion, and the centripetal force is provided by this QVB. Centripetal force is provided by this force QVB, which is the magnetic force acting on a charged particle Q. So now I hope the thing is clear that whenever the current flows through a current carrying conductor, it will having a magnetic force on it, which is given by ILB sin theta. If we are talking about a charged particle, then the force will be given by QVB sin theta. Done. Now this is an important rule. This is an important rule, Fleming's left-hand rule. Yeah, Fleming's left-hand rule is used to determine or to give us the direction of magnetic force. To give the direction of magnetic force. To give the direction of magnetic force on a current carrying conductor. On a current carrying conductor. So this left-hand rule, Fleming's left-hand rule, will give the direction of magnetic force. So what does that rule say? This rule says that whenever you are taking your three fingers of your left hand, one is thumb, one is index finger, and one is middle finger. So if I am taking the three fingers of my left hand such that three of them are mutually perpendicular to each other, you can see three of them are mutually perpendicular to each other. Yes. Then if this middle finger is showing the direction of current through a conductor, this index finger is showing the direction of magnetic field, then this thumb will give the direction of force. This thumb will give the direction of magnetic force on that conductor. Clear? So this is Fleming's left-hand rule, FBI. You can learn it as FBI. Starting with thumb, FBI. F for force. So force is represented by thumb. B is for magnetic field, represented by this index finger. And I is the direction of current given by the middle finger of the left hand. The basic thing is that you have to extend your fingers, all the three fingers, thumb, index, and middle, mutually perpendicular to each other. So this is the case. Yes, so now write the statement or see the statement. Whenever current carrying conductor is placed in a magnetic field, it experiences a force due to the magnetic field that we have learned. So the middle finger is pointing in the direction of current. Middle finger is in the direction of current. Thumb will give the direction of force that we have seen already. So what is thumb giving? Thumb is giving the direction of magnetic force. Direction of magnetic force. There is something known as index finger. Index finger will give the direction of magnetic field in which the conductor is present. Direction of magnetic field. And what about the middle finger? Middle finger will give the direction of current. Middle finger will give the direction of current flowing to the conductor. So these are the basic nomenclature, and all three are mutually perpendicular. All three are mutually perpendicular to each other. And as we are using left hand, as we are using the left hand to derive the relations, we will name it as Fleming's left hand rule. So Fleming's left hand rule is very important rule in deciding the direction of actually magnetic force acting on a current carrying conductor. Clear? So I hope this is clear that how the force is acting and how to decide the direction of that force acting on a current carrying conductor with the help of Fleming's left hand rule. With the help of Fleming's left hand rule. Now we'll see the questions. On it. So the first question. Yes, read the question. Okay. A negatively charged particle. Underline it. Negatively charged particle projected towards west is deflected towards north by a magnetic field. The direction of magnetic field is. So basically the force is given because see what was actually given, a negative charge particle is there. It is projected towards west. Suppose I am taking that as west. This is east. It is always good to make this diagram at the side of the question, so you can easily remember what is the direction. So a negatively charged particle projected towards west like this is deflected towards north. So this is the north. So if it is deflected towards north, can I say the force is along the north? The force is along the north. Clear? So the direction of magnetic field is being asked. What is the direction of magnetic field? So what can I say if negative charge is flowing like this? The direction of current should be towards the right, yes or no? Opposite to the direction of negative charge, yes or no? This is actually the direction of current. Now from the Fleming's left-hand rule, you have got F, you have got I. Can't you calculate B? So what we'll do, we will align the thumb along the direction of force, that is towards the north like this. Current is towards the middle finger. Middle finger is showing the direction of current towards east. This is north, upward, east. So this middle finger will give the direction of magnetic field. So magnetic field is inside, or you can say downward, because it is neither towards south nor east nor upward. It is downward. So the answer will be downward. Answer will be downward. Clear that how to use the Fleming's left-hand rule to arrive at the answer of direction of magnetic field? Examiner can ask any of the three things. Either he will ask direction of magnetic force, yeah. Either it will ask direction of current, or either it will ask the direction of magnetic field. Yes, but two things will be given in the question and third one will be asked. So you can easily decide the value with the help of Fleming's left-hand rule. Clear? Now next question is that the Fleming left-hand rule gives the direction of what? Yeah, this is a pretty much simple question. Magnetic field, current, induced current, no force. Yeah. So it is basically giving the direction of force. Fleming's left-hand rule gives the direction of magnetic force, or you can say the motion of the conductor. Yes. Okay. So I think the basic concepts are clear. What we have learned today, we have learned that whenever current flows through a current carrying conductor, then it is acted upon by a force which is known as magnetic force, whose magnitude is given by ILB sin theta, where I is the current flowing to the conductor, L is the length of the conductor, B is the magnetic field present, and theta is the angle between current and the magnetic field. Yeah. Then we see what is the force acting on a charge. Magnetic force acting on a charge moving with velocity v in a magnetic field B. That was given by QVB sin theta, where Q was the charge, V was the velocity, B was the magnetic field, and theta was the angle between velocity and magnetic field of that charge. Then we have derived, or then we have seen an important rule which is known as Fleming's left-hand rule, which is used to decide the direction of magnetic force on a current carrying conductor. It says that when you stretch these three fingers of your left hand, thumb, middle finger, and index finger, mutually perpendicular to each other, then thumb will give the direction of magnetic force, index finger will give the direction of magnetic field, middle finger will give the direction of current, that is FBI. Starting from thumb, FBI. Okay. So I think the basic concepts are clear. I hope you enjoyed the class. We have done this concept in the class, whichever we want to run this class. Yeah. But in case of any doubt, you can do one thing. You can visit the Ask IITians website. There is a doubt forum there. You can post your doubts there and it will be solved by our expert faculties. Okay. So we'll end this session here. Thank you so much. Stay safe and enjoy. Bye.